on to the last two talks. They're reproducibility talks. The speaker, please come up on stage. Sheng-Wei, Chen. Okay. This is one-class matrix factorization, point-wise regression-based or pairwise ranking-based.
Okay, hello everyone. My name is Sheng-Wei Chen, and I'm from National Taiwan University. I'm the first author of our work, one-class matrix factorization, point-wise regression-based or pairwise ranking-based. Let us discuss the one-class matrix factorization first. In the recommended systems with implicit feedback, we can only observe a few ground truths. In other words, the information of the user I likes or dislikes the item J is unknown in most of the IJ pairs. Please see the following example. And we have user A, user B, and user C. And item A, B, C, and D. And we only know the positive in those components, and the others are unknown. Therefore, one-class matrix factorization is one of the methods to handle the problem. Next, we discuss the pointwise setting for matrix factorization. We can use the ith user embedding, Wi, and jth item embedding, Hj, to accurately capture whether user I likes or dislikes item J. That is, Wi transpose Hj will approximate to 1 if the IJ pair is positive. Otherwise, we should estimate Wi transpose Hj to a small positive value, gamma 0, or even 0. The embeddings Wi and Hj are trained by least squares with traversing all IJ pairs in the user item matrix above. The reason that we set gamma 0 approximately to 0 is because most of the items are ignored or disliked by the users. That is, the unknown pairs includes lots of negatives. Okay, besides the pointwise setting, we discussed one of the state-of-the-art ranking-based methods for matrix factorization. The work number 1. They think the small positive value, gamma 0, in the pointwise setting is difficult to explain and design. So they propose a ranking approach that utilizes least squares to achieve the following approximation. We use red to denote a positive pair and blue to represent an unknown pair. For example, in user C, we then have 3 pairwise losses, item B to item A, item B to item C, and item B to item D. Their experiments show that for one-class matrix factorization problems, their ranking-based method is better than the pointwise method. Next, we talk about the reasons why we reproduce the work number 1. In the past, some works have shown that simple pointwise models are highly competitive with ranking-based methods. Also, the value gamma 0 can often be decided by the validation procedure. After the study, we found that the work number 1's loss is different from the standard ranking-based loss in supervised learning. In machine learning, if we hope that the red one is greater than the blue one, the loss function is often designed to satisfy the following property. The loss should approximate 0 if the ranking is correct. Otherwise, we should give the loss a value greater than 0. However, the work number 1's approach does not satisfy the property. For example, the first row gets the correct ranking, but still has a loss equal to 4. The second row has a wrong ranking, but gets the same loss as above. Okay. Here are our investigations. We show mathematically that the work number 1's approach is similar to the pointwise approach. Therefore, the performance between these two approaches should be close. After some effort, we reasonably reproduced the work number 1's results, but found some issues. First, they may report the best cross-validation performance, but not the test performance. Second, they use a more complex pointwise setting, different from the standard one. Third, they report NDCG at 200 and record at 200, but a smaller number of items are often recommended in practice. After fixing the above issues and conducting rigorous comparisons, we find that the pointwise setting is still competitive. In this table, we consider the matrix NDCG and record at 1 and 10 to compare the work number 1 setting and the pointwise setting. We can see that in many places, the pointwise setting is better than the work number 1 setting. Okay. In conclusion, for one-class matrix factorization, the simpler pointwise setting should be the first model to try. Okay. Any questions?
Thank you. We have time for a quick question. Okay, I have one here. If I got it right, you showed that mathematically there's some inherent issue with the ranking proposal that you reproduce here, and that it seems pointwise methods are still competitive, at least in the settings you tested them. My point is, it looks a bit counterintuitive to me that a pairwise method wouldn't outperform the pointwise ones here. Do you think it might have to do with the actual data sets you tested on? Do you see other situations in which this might not hold?
Oh, could you please ask the question again?
What's that? Sorry?
Oh, could you please ask the question again?
Do you think, to what extent the conclusion you draw in the end that pointwise methods are still highly competitive here has to do with the actual data sets you tested on? Would you expect different results in other situations?
First, because we are a reproducibility check paper, so we focus on the data set the work number 1 used, and we reproduce very carefully to achieve that, make sure the data set should be similar. So this work focuses on that data set. So, but in the past works, pointwise setting models did have a competitive results with ranking approach. So we believe that in some simple models, the conclusion should be also going.
Okay, let's thank the speaker again. And let's move on to the